Welcome to the Quantum Feedback Loop. I'm your host, James Myers, and I also publish the Quantum Record. In this discussion, I was excited to learn from astronomer Dr. Aaron Meisner about the search for brown dwarfs and what citizen scientists will contribute to learning from these curious objects in our solar system. Are they failed stars or more? I hope you'll enjoy our talk as much as I did. Well, Aaron Meisner, welcome to the Feedback Loop. We appreciate your time and look forward to hearing about your new citizen science project called Cool Neighbors.
Yeah, thanks a lot, James, for having me on. It's fun to always talk about this, so I look forward to our discussion.
Yeah, me too. Can you start us off with just an overview of the project before we talk about how people can become involved? So I understand Cool Neighbors will engage citizen scientists in looking for brown dwarf stars. And I've seen these described as failed stars with masses of up to 80 times that of Jupiter. What do we know about brown dwarfs, and what will we learn by looking for more of them?
Yeah, so I guess there were several parts to that question. As far as the origin of Cool Neighbors, we started a related project called Backyard World's Planet 9 in 2017, launched through the universe, and over the past 5 to 6 years now, that's become one of the most popular citizen science projects ever. And it's been a lot of fun. And so we wanted to do a derivative project of that called Cool Neighbors. The science motivation for Backyard World's Planet 9, the original one that we launched many years ago, is kind of split between two different science objectives. One being the brown dwarfs, as you mentioned, these objects that are kind of intermediate in several ways between the largest giant planets, like oversized version of Jupiter's, but they're also smaller than the smallest red dwarf stars. And so Backyard Worlds in part has been over the past many years looking for these brown dwarfs, which are very cold. So you need to look for them in the infrared, which is why we use all sky data from a NASA space telescope called WISE. But then Backyard Worlds also has a second objective, at least in the past it has historically, of looking for hypothesized planets in the outer solar system. These are sometimes referred to as Planet 9 or Planet X. And so what we wanted to do was to make a spin-off that we call Backyard World's Cool Neighbors, which is launching in late June of 2023. And the idea is to have it be entirely 100% focused on finding these cold and extreme brown dwarfs nearby the sun in our local cosmic neighborhood. And so there's several optimizations we've applied for that. One is that we now use machine learning to select our brown dwarf candidates for Cool Neighbors, whereas the original Backyard World's Planet 9 shows random sky patches. And we also show much more zoomed in focused versions of our image blinks of the sky to volunteers so that we can get a simple yes/no answer for each brown dwarf candidate in the long run to improve what we call our census of the sun's local neighbors. So by now we think we found all the very nearby stars to the sun because they're bright, but the brown dwarfs are faint. And so we actually don't really know if we found all the closest neighbors to the sun when you take into account the brown dwarfs.
How many brown dwarfs have been discovered so far near the sun?
Yeah, there's different ways of answering that question, it turns out, because discovered tends to be a little bit of an overloaded or ambiguous term. So there's something like 3,000 or 4,000 known brown dwarfs that have been discovered and have been very detailed confirmation. They have very detailed confirmation so that we know for sure that they are brown dwarfs based on their spectra. There's other categories of objects that we're pretty sure based on the fact that they're moving, which means they're nearby, and that they're red, which means they're cold, that they must be brown dwarfs. And so that's another similarly large number. So for example, within Backyard World's Planet 9, we've already discovered about 4,000 very clear-cut brown dwarf candidates, but we don't have the full follow-up confirmation on every single one yet. But the answer is several thousand.
Well, and how many people were involved in or are still involved in Planet 9?
Yeah, so in the Backyard World's Planet 9 version of the project, we have a little under 80,000 registered users.
Wow.
Thing is, though, that you don't actually have to register on the Zooniverse portal that we use in order to contribute. So we estimate that the number of actual contributors is something like a factor of 2 or 2.5 larger. So we think in the 150 to 200,000 unique contributors. And then within that broader group, there's something like 300 to 400 of what we call advanced users or super users who have voluntarily given us some of their contact information. Then we stay in very close touch with them for example, with weekly calls, and they do all kinds of stuff like writing telescope proposals, writing their own papers. So a lot of our science comes from the interaction with that subset of super users.
Well, that's really impressive. And these are people from across the world.
Yeah, our super users are quite diverse geographically, and they also have quite varied backgrounds, ranging from, retired engineer, high school student, middle school student. There's a fair amount of representation from the tech industry, as you might imagine in a data analysis project like this. There's definitely folks from tech who have some really interesting and valuable skills, especially in areas like machine learning or data science, that they can come in with this kind of new perspective and discover things that professional astronomers using more traditional techniques haven't found before.
That's really neat. And I guess we'll talk in a little bit maybe about how people will get involved in your new project, Cool Neighbors. I wanted to just ask maybe about the machine learning though, because I guess what you're doing, from what I understand, is you're taking the infrared data or the data of the infrared that's been observed and feeding it into algorithms, I guess, which pick out likely candidates. Is that how it works?
Yeah, exactly. So that's kind of the novel new thing we're adding into the mix for Cool Neighbors as compared to the original Backyard Worlds Planet 9 version of our project. So the way this works is that there's tens of trillions of pixels of data from this NASA Y satellite. It's up there taking images of the sky, 2 megapixel size images every 10 seconds, actually, all day and all night. So right now, as we speak, even. So a huge amount of data. And then for Cool Neighbors, the specific type of machine learning that we use is deep neural networks applied to this pixel data. And so we send essentially little patches of the sky that are like time series videos. And we have this neural network that's trained to identify moving objects on that input. And so we have some set of, say 250,000 candidates that get output by this machine learning algorithm that we think may be brown dwarfs. And then we want to upload those to Zooniverse so that the Cool Neighbors participants can visually inspect them and review them and tell us which ones look good and which ones are less promising, because we wouldn't just go directly from the machine learning to using the premier telescopes like, Keck or Gemini. We definitely want to insist on having some sort of detailed review process to make sure we're not looking at something that's simply noise in the image.
And what's the value of human participants in this sort of thing? I mean, I remember it was the Galaxy Zoo project that I heard of some years back, where it was said that the machines were good maybe at identifying candidates, but not so good at identifying the patterns that actually determined which ones are actually, in your case, I guess, brown dwarf stars. So is that what the human is adding to this aspect, is pattern recognition, or is it something else?
Yeah, I think there's a couple aspects to that. One of them is just the simple pattern recognition of the fact that we're looking for moving objects in time series movies, which is something that humans are really good at. So there's just that basic level of it. There's also just a huge acceleration factor that comes from doing this crowdsourcing approach. Because if we think back even only like 5 or so years ago, I remember one of our team members did an analysis like this where he had some automated algorithm with code that gave him 1 million candidates for brown dwarfs. And then he personally looked through all 1 million of those. And wouldn't it be better and faster if we just had 10,000 people each look at 100 of those? That seems like a natural thing to do, given that you don't need a PhD particularly to see something moving in an image.
Yeah.
So I think there's a big gain from that. But then the other side of it, which is a different kind of pattern recognition, I guess, is that what we found is that often the most interesting discoveries aren't exactly what we thought we were looking for. And so it really helps to have that human element of someone going in and saying, well, this looks like it's moving, but there's also this, which is weird, which we've never seen before. And so that can be really useful in terms of sort of like discovering the unexpected, I guess you would say.
No, that's amazing. Actually, that's really neat. I would personally look forward to participating as a volunteer in the project. So, apart from identifying brown dwarf stars, what is it you're looking to learn about these stars? Like, I guess what's known about them now, and what do you think might be discovered? What new knowledge will be added as a result of this?
Yeah, that's a really interesting question. there's a lot we don't know about these brown dwarfs simply because of the fact that they're so cold and so faint and so red that it makes them hard to observe with small traditional telescopes in the visible light part of the spectrum. What we do know is their sort of temperature range, which again falls in between the hottest giant planets and the coldest stars. We know a little bit about their mass, although it's very tricky to get brown dwarf masses because these objects, they aren't like stars where they're powered by fusing hydrogen. They're formed initially, and then over time they cool and release energy. And so there's this degeneracy between the age and the mass and the temperature, which is hard to break. But what we do know is, these temperatures and some occasion masses, which again put them between the smallest stars and the biggest planets. We know something about the atmospheric chemistry as well. So for example, water absorption is very prominently seen in the atmospheres of certain kinds of brown dwarfs. And, in the brown dwarf research community, we often find this amusing because there's so much energy and time invested in trying to detect water in these giant exoplanet atmospheres. And yet we can't help but detect water all the time in these brown dwarfs. And so there are deeper questions, though, that brown dwarfs can teach us about, and also that we still need to sort of learn about with respect to brown dwarfs themselves. So one of them goes back to what I was just saying about exoplanet atmospheres, which is that because the coldest brown dwarfs overlap in temperature and mass with the coldest giant exoplanets, they can be seen as like these laboratories that allow us to gain new insights about the atmospheric processes in exoplanets, but in a way that's much easier to do than with the exoplanets, because of course, when you have an exoplanet, it has a host star, which is much, much brighter than it typically. And so it's very, very challenging to make these measurements for a giant exoplanet. But if it's a brown dwarf just wandering around interstellar space alone, that's much, much easier. The other kind of deep mystery is the one about star and planet formation. We don't really know how brown dwarfs form. Do they form like Jupiter and then get ejected from their host star system? Or do they form like stars, but just stars with lower mass, and so they're colder? And that would be a very interesting topic to delve into, because it gets at this whole question of where is the boundary of a star versus a brown dwarf versus a planet, right? We had this whole what is a planet debate with Pluto, which reminds me of the Planet Nine thing again. But now you have kind of the same thing at the boundary of the brown dwarf versus giant planet. And is it a formation mechanism thing? Is there something else that distinguishes them, or are they just essentially the same objects? We don't really know.
Interesting. And so I guess from what I understand, a planetary formation, even Jupiter might have a kind of a rocky core, I guess, and then just this massive gas around it, whereas a star would form by intense compression of gas, I guess, and ignition of that into a fusion process. Is that the difference between a planetary formation and a star formation in a nutshell?
Yeah, something like that. The way I think about it is kind of like, I think of a star forming from the collapse of this molecular dust cloud, essentially. And so we know that's how stars form. And so you can imagine that maybe the big molecular cloud also just has smaller fragments, and those become smaller objects, which we call brown dwarfs. But the alternative is that a brown dwarf forms like a planet, in which case it's really forming out of a protoplanetary disk around a star or a protostar, rather than directly out of that collapse of the molecular cloud.
Right. So like a disk of rock and dust and all of that, I guess, just compressing into a planetary core.
Yeah.
Yeah. Okay. And then you mentioned water, and water being a signature of life. You're not actually expecting to find any life in the brown dwarf itself, I guess, but you're saying that it will allow us to understand more about how water gets into the atmosphere, so that when we're searching for exoplanets and potentially life, we'll know more about that. Is that the case?
Yeah, as far as the brown dwarf research community, we tend not to hype up the search for life aspect of it. But now that you mention it, I do feel like it is something that potentially we could play up a little bit more or emphasize a little bit more. Because the fact is, we do expect that there are satellites around some of these brown dwarfs. By satellites, I mean natural satellites, not necessarily made
Not
by some
human made. Yeah.
extraterrestrials.
Yeah.
Um, in which case, there's this whole debate about, are those exomoons, are those exoplanets? But we do expect there to be satellites, just like Jupiter has some large moons. And yeah, so I mean, this is all very deeply connected with the whole, search for other systems that could potentially harbor life, exomoons, exoplanets. But we tend not to play that up as much as the exoplanet community for whatever reason.
Yeah. Yeah. Interesting. Well, no, that's great. And so just before we talk about how people will get involved in the process, I'm just wondering if you could sort of take us back to what led to you to start the citizen science projects, the backyard project in the first place, and sort of how does that relate with your work? Maybe if you could just tell us a little bit about your work at NOIRLab and your previous use of the WISE telescope that you mentioned.
Sure. Yeah, so NOIRLab stands for, it's a rather long acronym, but it's NSF's National Optical Infrared Astronomy Research Laboratory. And so what we do is we manage the nighttime ground-based optical and infrared astronomy for United States and particularly NSF resources. So you can kind of think of us as being like the US National Observatory. And beyond just operating telescopes, though, we have a variety of functions, including managing how telescope time is allocated to different scientific research groups, also outreach or engagement with the general public, for example, protection of the night sky from light pollution, for example, from cities or from satellite constellations, for example. So there's a wide variety of roles that we play. But one of the unifying themes that's going on across astronomy, and it's definitely something we are very involved with in NOIRLab, is the way that astronomy and science in general are becoming very data intensive and very data driven. And so we have essentially like a data science department here as well. And I personally work on something called the Rubin Observatory, also known as LSST, or at least that used to be its name. And this is kind of looked at as like the prototype or the next big thing in the category of big data in astronomy, because it's the largest ever digital camera and it's going to be taking millions of images over only a few years. And so we're talking many terabytes of data per night. And so all of this I view as being kind of related back to the theme of how astronomy is becoming so data oriented. And so my interest has always been in like the data analysis side of things. And so for many years, I had been working alone to analyze, as I said, this hundreds of trillions of pixels of WISE data. I had been processing them at a DOE supercomputer. It's in Berkeley, California. It's called NERSC. And I had been downloading every single image that the WISE telescope had been taking, which by now is like 40 million images, each of which has 1 million pixels.
Wow.
I've been processing to make all these custom built sky maps of the entire sky. So they're kind of like the deepest and best ever looks at the infrared universe. And I had various ideas about how to mine these. And for a while, I had kind of thought, well, maybe I can just write some code and run it on the supercomputer and discover all this cool stuff. But then Mark Kushner from NASA came along and was like, why don't we do a citizen science version of this where we just show all the images to everyone? There's plenty of images to go around. There's probably plenty of discoveries to go around. And it did turn out in the end that it was much more scientifically productive and also very fun to go the crowdsourcing route rather than trying to be something where I alone type some code on my computer to discover things.
That's a really interesting story, and interesting to hear about that new level of data that's coming. So is the Rubin camera actually producing images now, or has it come online?
Not quite yet. It's getting very close though. Like the whole telescope structure is essentially now built. The camera is entirely built, so it is now the world's largest digital camera, which is awesome. But the camera hasn't yet been officially mounted on the telescope.
Okay.
And so over like roughly a year-ish is the timeline for when we'll start getting the first pictures of the sky on the telescope with this huge mirror with the biggest ever camera. So we're still a little ways away from that, but there's a lot of work ongoing already to prepare for that on the data side and also on the citizen science side as well.
Well, so those images will feed into the data eventually for the brown dwarf search project?
Yeah, we don't have, say, a specific plan or specific funding for that yet, but I could certainly imagine that happening. One cool thing that Rubin Observatory is doing on the public engagement outreach side is that I think this is a very smart idea. They've set up what essentially is like a pipeline directly from this huge amount of Rubin LSST data to the Zooniverse. So they have a partnership with the Zooniverse on the sort of data pipeline side. And what that will do is it will hopefully allow lots and lots of scientists or even citizen scientists to quickly launch their own citizen science projects, which I think is a brilliant idea, because why it sounds much better to make it easy for lots and lots of different projects to get launched rather than to just say at the start, oh, we'll have one project about asteroids and one about galaxies, and that'll be that. Like, I really like the idea of like building the tools and then letting the community have at it with their imagination and their creativity as far as like what the actual projects are.
It'd be really interesting to see how that evolves over time, I guess. Yeah. Maybe if you could take us through the process. So if somebody wants to become involved in the Cool Neighbors project, maybe just give us a high level of what the steps would be. Do they need any special knowledge? Do they need any special equipment? How much time do you think this will take? Are they interacting with each other?
Yeah, that's all good questions. So by design, we hope that it's very simple to get involved. You simply go to coolneighbors.org. You could do this on your internet browser, on your laptop, or even on like a smartphone or iPad. That being said, this does sort of impose a requirement of having an internet connection, in which we realize. So that's the one thing you really need. On the other hand, I would argue that's a much lower barrier than some past forms of amateur astronomy, like having a backyard telescope. A lot more people have an internet connection and a phone or an iPad or a laptop than would have some custom rig in their backyard to look at the sky. But you just go to coolneighbors.org. There's a field guide, a tutorial, an FAQ. There's various informational tabs like that you could read through probably in like half an hour, maybe an hour at most, just to get a flavor of what we're going for. You can optionally sign up to have an account with Zooniverse, but you actually don't even need to do that. You can contribute classifications on our site even without registering, which I think is great. And then what you'll do is you'll click classify is what it's called, or you can just directly click on an image from the homepage, and that will start you off looking through a series of these image blinks. And what all you do is you answer a yes/no question to say whether what you see in the middle of the image looks like it's moving or not. And so we tried to make this as simple as possible because we think that will help with the downstream data analysis and the data mining to have a very clearly defined task.
Okay, so and you're presenting, I guess, different sectors of data to different participants.
Yeah, our current plan is to have about 30,000 sectors of the data, and then that'll equate to roughly 600,000 classifications, we call them, which is one instance of one person looking at one of these and rating it.
Okay.
So we'll have to see how long that lasts. We do have a little bit of a concern that we might go through that 600,000 too fast, so we're trying to be ready with more data. But yeah, the idea is that we do have a lot more candidates to look at if we do burn through those real fast. So at least a factor of 10 more.
I guess that would be a good problem to have. So if I and I want to volunteer for this project. So when I volunteer, am I required, like, are you looking for any time commitment, or is this something I could do once a week when I have time, or how does that work?
Yeah, there's no minimum time commitment at all, really, other than the minimum unit of contribution you can make is one of these, what we call classifications, which is giving a yes/no answer to one of these image blinks. And I would expect that takes less than a minute, so maybe 30 seconds, or once you've gotten used to it, maybe 15 seconds per classification. There's no need to like do this on a particularly regular basis or for like continuous intervals. Like, it would be perfectly fine to randomly do one at a random time every other day, for example. Every contribution is great and it's appreciated. Going back to one of your earlier questions about interaction, there's also no requirement necessarily to have interactions or discussions with other participants or with the science team, although the Zooniverse interface does have something called a talk forum, which is essentially for each movie of the sky, it has a little section beneath it where you can write a comment if you find something particularly interesting or exciting about it. And then, for example, maybe someone from the science team will come back and say, oh yeah, that looks great, or like, here's what I think is going on, or with your fellow volunteers, you can try to sort things out.
Will the volunteers have any way of knowing the results of what they're doing while they're doing it, or at any interval of their participation? Or is it the sort of project where you need to get all the data first and then figure out what the result is before you can get back to the participants?
Yeah, that's a good question, a really important question, I think. It's something we've pondered a lot too, because we'd like to get everyone immediate feedback, right? Because A, it would help to improve our results, I would think, and B, it would just be the right thing to do as far as giving people guidance and giving them attention to improve their experience and improve the results. So right now, the main way to do that is we have moderators who are kind of like advanced users. We also have science team members who can go on to this talk forum chat platform and have discussions with you. We don't need the full data set to give feedback already. We actually, within the subjects, within the list of the movies that we're showing people, we have some known brown dwarfs, for example. And so we do have some sort of truth data in there where we think that'll help a lot with the feedback. But I do think the feedback is a really interesting area where there could be a lot of improvement in the near future, especially if you think of this as something like an artificial intelligence or AI coaching bot or something like that. That would be really, really cool to see embedded within the Zooniverse interface. I don't know if that's something that's already being developed or not, but I can imagine that having a huge like game-changing potential to sort of have 80,000 advanced users instead of 400.
Yeah, very cool. And I mean, we're certainly interested in following the project over time as it goes along and finding out how it evolves. So we'll certainly be in touch during that time. I wanted to ask, I know you're using infrared data, and the James Webb Space Telescope uses, that's what it's sensing. Is there going to be any tie-in to the Webb telescope and its data?
Oh yeah, definitely. There's a big tie in there. So, for several years when we were running the Backyard Rules project, we would always write in our proposals, or we would always write in our press releases, this is really important work because we need to find the weirdest, the most extreme, the coldest, the most planet-like brown dwarfs so that we can look at them with James Webb Telescope. And then lo and behold, in the first cycle of JWST observation, cycle 1, our Backyard Worlds team did actually get an approved program to look at about a dozen cold and unusual brown dwarfs nearby the sun. And so that data has been rolling in now. And at least one or two of our citizen scientists are co-investigators on the JWST proposal with us, which I think is awesome. And at least a few of the objects, the brown dwarfs on that program that have been observed by JWST, were discovered originally by our citizen scientists, which is awesome to think about. And then just recently, for the second cycle of JWST observations, we got another citizen science discovery approved for JWST observations. This is a program that I led. It's for a very, very unusual brown dwarf called the accident, is what we've nicknamed it. That is a formal term that we've used in the literature. And that has a particularly strong connection to cool neighbors because we think this is a very ancient member of the Milky Way's halo. And these are exactly the type of extreme, fast-moving brown dwarfs that we're looking for in cool neighbors. So hopefully we'll find more like that with cool neighbors and be able to get more JWST time to look at them.
Look for more accidents. Yeah, that'd be neat. Well, that's really cool. So anybody's interested in the project, they just have to have an internet connection, computer, an eye for motion, I guess. They're looking for moving objects on the screen. That's essentially it.
Yeah. Right now, the project only exists in English, I believe, but with Backyard Worlds, we've had it translated by now, in some cases by our volunteers, into many different languages. So we do hope that over time we'll build out a profile of more languages in which it's available.
Well, that's great. We wish you a lot of success in this. And as I say, we'll be really interested in following up on it and seeing how it goes. And I look forward to participating in it. And I hope many others do as well. So, Aaron, I just wanted to thank you for your time. And this is really exciting. I'm looking forward to seeing how it turns out. So thanks for taking the time to explain this to us.
Yeah, thanks a lot for taking the time on your end to chat with me about this. It's always fun to have these types of discussions. And yeah, I definitely agree. It's always great to try to reach out and recruit more volunteers and get more participation and spread more of this learning about astronomy, but also make hopefully more discoveries as well.
For sure. And we will be in touch to see how it goes. So thank you again. We'll look forward to talking to you soon. Our thanks go to today's guest and to you for listening to the Quantum Feedback Loop. You can find more information about this discussion in the Quantum Record at www.thequantumrecord.com. Please subscribe to this podcast wherever you get your podcasts, and join us for more fascinating discussions with the people who are pushing the limits of knowledge today for the benefit of tomorrow.